today we are going to talk about two main types of collisions. Inelastic, where two things or more things come together and stick together and move off as one, and elastic, where things come together and they bounce off. Now in nature, most objects will be mostly inelastic, although certainly you can consider two cars hitting and bouncing off each other. It's not fully inelastic, but it's also not fully elastic, and we'll talk about the differences. We're going to start out with the simpler of the two, inelastic collisions. These are the ones, these are the ones, what? Okay. These are the ones that stick together. So you have one or more objects initially moving. We'll say M1, V1 initial. And that's going to collide with something else. They could be going the same directions, just at different speed. They could be going opposite directions. Let's just take, for this case, going opposite directions, V2 initial. So each is going to have its own initial velocity. Direction's important with this because both velocity and momentum are vectors. And then after they collide, they're going to move off in some direction and have a combined momentum of the sum of the masses times that final momentum, whatever it is. Okay, so this was the case where you had the two carts coming together and sticking, and all of them behaved more or less in a similar fashion. I don't know if this will show up on the video, but maybe you should have come to class. They know who I'm talking to. What's that? Burned. Virtually burned. Okay, so these two things hit. It's got a momentum ahead of time. This can be a zero momentum. One of them certainly could be ahead of time. And they hit and move off together. So this was our first lab. Looking at the data, comparing the initial values to the final values, is momentum before and after conserved? So is your initial momentum very similar to your final momentum? We can be off by a little because there's friction and stuff. Yes, you got somebody over there, you got a similar number? Are you seeing similar numbers fairly close to one another? Pretty close. Momentum here is conserved. So what that means is if we sum up all of the momentum, which we could use a sigma for because they don't get used enough. M initial, oh, that's no good, I'll do N. I'm going to use an I here. If we go for all of the N's, our sum of all of the masses times their individual velocities, whatever those are. It could be two things, it could be lots. That's going to be equal to the sum of their masses times their final velocity. And there's only one final velocity because they're all moving up together.
And what is
N is, I don't practice my math enough. N is just the iterative thing. So it's 1, 2, 3, 4, 5. However many you have. And so this would be M1 plus V1 initial plus M2 and V2 initial and so forth. And then over here, it's all of these masses, M1 plus M2 plus all of them, times whatever their final velocity is. And so you could have two. We're going to keep it to 2, maybe 3 on a homework problem, but I don't want to stress you out too much because it just gets long and doesn't really aid in learning. So momentum, though, is conserved. And this is what we can say because of that. What about kinetic energy? Are your kinetic energy values before and after the collisions about the same, or do they vary widely? Yours are the same?
I'm saying it should be the same.
Well, you don't know what if they should be or not. Well, but we did an experiment to see. Alex, you're shaking your head no. Look at your kinetic energies before and after on that Lab 5A. Are they the same? Are they a factor of 2 or more different? Because if they're relatively close, we could probably say close enough to fudge it, given our experiment. But if they're twice the difference or 10 times, I'm not concerned. So what do you think? What's that?
No.
No? You say no, you say no? No. They should be fairly different, much more different than the momentum. Because kinetic energy is not conserved. Now, energy is conserved, but it goes into other forms. And we can think of this, a good example of this would be, let's take 2 of the same sized carts and push them together, each going the same speed. I can get close to this, probably not exact. But if both of these carts, they still have the same mass as each other, if they're going the same velocities toward each other, what should happen when they hit? Should stop. Let's see if the math works out for that. So let's do an example.
Is there magnets in the parts now?
Yeah, doesn't that kind of...
No, it actually doesn't. Yeah, because you're putting, there is energy in the magnets, but I see what you're saying. I don't know any better way to do it with these cars. But let's just see what the math shows us first, and then we can go through and explain any more questions. Example 1, 2 cars, we'll say half a kilogram each, strike each other going 1 meter per second in opposite directions. What's their final and in opposite directions in an inelastic collision? What's their final velocity? To solve this, we're going to use the conservation of momentum that our experiment showed us. We'd say, okay, the momentum of the first part, m1, its mass times its initial velocity, plus the momentum of the second one, m2, times its initial velocity, must be equal to the sum of their masses times whatever the new final velocity is. So we have a mass of each of them, 0.5 kilograms, 1.0 meters per second, as many as I could do. Equal to the sum of their masses, which will just total out to 1 kilogram, times whatever their final velocity is. Now, these are vectors. Velocity and momentum are vectors. So what do I have to be careful about when I'm writing those? One has to be negative. It really doesn't matter which one. If you say one direction is positive, the other is negative. So if I give this an initial velocity in the positive direction, since this is in the opposite direction, it must be negative. What sum do we have over on the left side? 0. which means our velocity must be 0. And that is what we had observed there. Now, to look at this for kinetic energy, if we're looking at kinetic energy ahead of time, that's going to be 1/2 m1 times v1 initial squared plus 1/2 m2 times v2 initial squared. And I'm just going to put in values there. Squaring that means that it takes away the negative sign. So we'd have the 1/2 times our mass, 0.5 kilograms, times the square of our velocity, 1 meter per second. And then we'd add it again, so it's times 2, essentially. So beforehand, we have 1/2 times 1 times 1/2 is 0.25, and then multiply it by 2, so we'd have 0.5. The units here would be joules. But afterwards, both of them stop. How much kinetic energy do we have then? 0. So we lose the kinetic energy. It's not conserved in this. But we never, and this will be true for everything we look at, so keep that in mind when I ask you the next question, the same question on the next one. We never lose momentum in the universe. This is probably the most fundamental law, the conservation of momentum. We see that it's conserved here, we'll see that it's conserved in the next one, and it will be conserved in every single interaction that you see. But kinetic energy, that can go into different things. So very often, we'll see two things they stick together. That energy goes into deforming things. Or, as you guys have noticed, it goes into kind of a potential energy buildup in the magnetic fields. So if these magnets are going to try and repel, it's going to take some energy to get them together. That can come from the kinetic energy. And likewise, even if they attract. Okay. Any questions before we move on inelastic collisions? If you can remember that they stick together and the momentum is conserved, you'll be okay. Just add up the momentum before the collision, and that's got to be equal to the momentum after the collision. Okay, let's look at lab B then, elastic collisions. These are the collisions where two or more things hit and bounce off each other. So we might have two things going right straight at each other, V2 initial, 2, and then boing. Okay. That's not going to get old. They have their own final velocities because they're now going in the opposite direction. And there are lots of different things that can occur with this, and I'll try and simplify it as much as possible. Okay, I already gave you the answer to this, but look at your data. Is the momentum from before the collision similar to the momentum after, and maybe a little bit higher before? Or is it vastly different? About the same? About the same. Should be similar. Probably a little lower again because there is some friction, and that slows down the cars from between the collision and when measured. Momentum again, as it is in everything, is conserved. So what that means is we can say the momentum before this, which would be the product of the mass and its velocity, and then the other one, must be equal to the sum of those momenta afterwards. So M1 would be moving at V1 final M2 would be moving at V2 final. So that's got to be true. And they aren't stuck together anymore because they can move off at separate velocities. Looking at your kinetic energies before and after the collisions. Are those close to one another? And especially keep in mind how far apart they were for the first set. They were a factor of 2 to 5 usually, I think. Different in that set. How close are they? Are they close enough that we could say, maybe conserve? Carter says yes. Yeah. Kinetic energy in this kind of collision is also conserved. Now in nature, it's really hard to see a perfect collision like this. When we see them in like at macro scale, like cars and things, it's really somewhere in between. But if you start looking at atomic things, atomic interactions, those bounce really well. What this means though for us is that if we took the kinetic energy before the collision, 1/2 m1 v1 initial squared, 1/2 m2 v2 initial squared, that's going to be equal to the kinetic energy afterwards, which would be, using our terms up here, 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So then to find if you know the velocities beforehand, well, then it's just a simple thing to solve these two equations with two unknowns, the final velocities. Some of them are squared. It's just a simple math trick. It probably will only take you a page or two to solve that. Simple math. And I'm not actually exaggerating on that at all. It can take 2 pages to finish that, and then by the end you've made some error, so it's not right anymore because the terms are huge. So I have a little bit of a simplification for you. Not that this is fun, I don't want to take the fun away from you. There we are. So this thankfully has been solved for us by people who like that sort of thing. So if we've got 2 objects coming in, colliding with each other, we know their initial velocities, we can say the following. And here's what you'll want to use for when there will be a homework problem or 2 like this. If we want to find the final velocity of the first one, we take m1 minus m2 over the sum of those 2 masses times v1 initial plus twice the second mass over the sum again times the second initial, v2 initial. That'll tell us how fast the first card is going. Second card is twice m1, sort of the reverse of this. m1 plus m2, v1 initial plus m2 minus m1 over their sum times v2 initial. We're going to apply this on some of the cases to make sure that we're getting kind of a similar result to what we saw in the experiment. Settle down. So let's take a case where we have 2 things coming in. let's make it simpler by saying our V2 is going to be 0, our V2 initial. So our second cart's going to start out at rest, just like in our experiment. Our V, they're going to have the same mass too, because that'll make it easier on us. I'm going to push this cart in at some initial velocity. Let's predict what the final velocities will be if they have the same masses as each other. The V1 final here. We've got a term of M1 minus M2. 0. Okay, this term goes away. So it's determined by the second term, which is 2 times the mass of the second one over that times the initial velocity of cart 2. What's cart 2's initial velocity? 0. So we have a 0 plus a 0. It's predicting that our first cart will have a 0 velocity after the collision. Second one, we've got 2 times at the mass of the first cart over the sum of the masses. But these masses are the same. So this would just be 1 times our initial velocity. Then over on this term, we've got the mass 2 minus mass 1. They're the same, so that's 0. So that term goes away. So what this is predicting is that if I push 2 carts of the same mass together, with the second one starting out as 0 velocity, the first one should stop, and the second one should continue at the same velocity the original cart had. We'll give this a go. Reasonably close. This one kept moving a little bit, although it might also have been a little heavier. Boing. Pretty darn close. Okay, let's take a case, talk with someone next to you. I'm going to load up the first cart with a bunch of mass. So the mass of cart 1 coming in is going to be much greater than cart 2. Cart 2 is still not going to be moving. So take a moment with someone next to you. Predict, what do you expect to see for the 2 velocities of these carts afterwards, with mass 1 being much, much greater than mass 2, and velocity 2 starting out as 0.
Just go on to Snapchat.
And Reese has her
I will, for the most part, if a former student that I had a relationship during school with, especially in physics usually, sends me a friend request, I will almost always accept it, but I typically don't go out and look at it. Okay, what do we expect for these? What do we expect for the final velocity of our heavy, massive cart? Let's look through it. So if this is something, if M1 is much, much bigger than M2, what's something really big minus something really small in comparison?
Something that's really big.
But practically as really big. And then that's over something really big plus something really small. Just slightly more. So we have something slightly less than M1 divided by something slightly more than M1. Just a little less than 1. But it's about 1 times that. And then we've got 2 times something really small over something big plus a little bit. Something really, this is really small. So, and that's also an initial velocity of 0. So this term's not going to affect it at all, but even if number 2 is coming in, because this mass is so much bigger, it wouldn't have much effect. So what we should see is a speed a little bit less than this, but pretty darn close. Let's look at 2, which started out, it's the smaller mass and it started out as still. So again, we can ignore this term because it's going to be 0. But we have 2 times that big thing divided by that big thing plus a little. What's 2 times a big thing divided by a big thing plus a little? About 2. A little bit less than 2. So we'd expect a little bit less than twice the initial velocity of our first cart. If this weren't 0, it'd be something negative, right? M2, a little thing minus a big thing over approximately that big thing. So that'd be about -1. So it'd be slowed down. but this is still probably going to be the big one. So let's see. We have a request for a big one, although it's going to knock off my weights, but we'll give it a go. Okay, but we saw what we predicted, that this one slowed slightly, but that one took off at a faster rate. Okay, same thing, but let's flip them. Let's put all that weight onto our stationary second cart, make your prediction the same way, and see what happens. Predict. Very tough. Yeah. Tell multiple choice.
Are you going to put the two
10%.
questions? Are you going to put the scientific law and theory on the test? So when you say multiple choice,
Let's talk about that a little bit later. Yeah, four or five. I think 4.
Oh man.
Okay. So darn it. Let's predict. We've got something light coming in with some initial velocity. That one's going to be 0 come hell or high water. So we can, again, ignore these two for now. Let's see what we're going to predict for the two afterwards. There, see, it found a little bit. So the final velocity for this one. It's m1, the small one, minus the big one. So those two together are going to be approximately minus the negative times the big mass, divided by the sum of the two, which is only a little bit bigger than this. So that'll be about minus m2 over m2. About minus 1. So that's predicting that it'll end up with a velocity of minus 1 times its initial velocity. What does that mean? Going to bounce back at approximately the same speed. Okay, then we have twice for the final velocity of this one, 2 times m1, which is still a small number, divided by m1 plus m2, which is a big number. So 2 times a small number over a big number. Very small number. Almost 0. Very small number times that. And then, again, since the initial velocities are 0, we can ignore that. So we predict this one to go in the same direction. It's positive number as the original push, but at a very low speed. And then this one should actually reverse and go back at approximately its original speed after the boing. Very good. Oh, it still worked.
make the weight fall
Light it on fire. So 2 big things to remember about collisions are that this will work only for elastic collisions, because this is a solution to these 2 observations that both momentum and kinetic energy are conserved. But if you have an inelastic collision where they stick together, it's actually a lot simpler. All you have to say is that the momentum beforehand, which are separate, is equal to the momentum afterwards, where the 2 things are together. So usually you'll only have one thing to solve for, that V final. Conservation of energy actually works in any situation. We've talked before about if you've got a big person and a little person pushing against each other, like on ice, the little person's going to go a lot faster than the big person. Think about that. That's not a collision, but it's an interaction. If they're standing there, what's their momentum beforehand?
0.
Should be 0. So momentum before must equal momentum after. So if they have 0 momentum before, well, both of them are moving, right? So you'd have a big mass times the velocity, the big mass final, plus a little mass times the velocity of that person. What has to be true about those 2 velocities? There are a couple of things we can say.
Like, one has to be moving in the exact force opposite the other.
One has to be moving opposite. So one would have to be sort of the negative direction, The other would have to be positive. If this is, say, me and my daughter, I outweigh her by about 4 times. If my mass is 4m and hers is m, what can I say about the velocities? 4 times more. So if I move at a velocity of v, negative v, she would be moving at 4v, like that. Because our momenta have to be equal before and afterwards. There are a couple of questions along those lines. So this doesn't only apply to collisions, but it does also apply to collisions. I think